Hey everyone, and welcome to our 3.3 lesson, which we can see is on transforming to achieve linearity. So at its base, we know this word transform means to change, and then it says to achieve or accomplish linearity, with that base word being linear. In 3.1, we learned about scatter plots and correlation and talking about if the form is linear or nonlinear. And in 3.2, we talked about our least squares regression line, or in other words, our line of best fit, or even more simply put, a line that matches the points within our scatter plot. That's really what our least squares regression line is. It's a single line that best summarizes our scatter plot and fits our data the best. Okay? But I think we all understand that not all relationships that exist mathematically are linear. There's different types of mathematical relationships. So when we encounter those, what do we do in order to achieve linearity? Remember, correlation only works for linear relationships. So if we have something that's not linear, what can we do to make it linear? And that's what we're going to learn about here. So only two learning targets here. We can see our first one says that students should be able to use transformations involving powers, roots, logarithms to create a linear model that describes the relationship between two quantitative variables and use the model to make predictions. And then number two, determine which of several models does a better job of describing the relationship between two quantitative variables. So if we have 2, 3, 4 different models for a relationship, how do we determine which one is the best to use? Okay, one thing before we go on, students see this word logarithms and they think logs, natural logs, things of that nature, kind of gives them some PTSD from pre-calc. Okay, we will not be doing any actual mathematics by taking logs, solving logarithmic equations, stuff like that. So if that's the case, don't worry about it. If you're freaking out about that, not going to have to worry about that here. Okay, now for our opening activity, what I'm going to invite that you do, and you'll have to pause the video for it in a second if you choose to participate, is to just take out a scratch sheet of paper. So go ahead and pause the video now until you've got your paper out, and then you can resume. Okay, now theoretically, if a single piece of paper could be folded in half 50 times, I want you to predict about how tall would that piece of paper be once it was folded up. If you put it on the ground, okay, would it be 1 inch? Would it be 1 foot? Would it be 10 feet? Would it be a mile? What do you think it would be if you took a piece of paper and folded it in half and then took that and folded that in half? Okay, and again, I say theoretically because you can only really do that 6 times probably, if that. And so if you want to, go ahead and fold your piece of paper those 6 times, get an idea as to where you're at after 6 folds, and then make your guess. Okay? Pause the video if necessary. Now, a standard piece of copy paper is 0.004 inches thick, very, very thin, which we're not surprised by. So use this information to fill out the table below. So if number of folds is 0, if we do not fold the piece of paper, the height, or in other words, the thickness of our paper is 0.004 inches if we just laid it flat on the ground. Now, if we fold it in half one time, we have 1 fold. Well, essentially what we've done is we've taken that original thickness of 0.004 and we've doubled it, because now there's essentially 2 layers of paper after we folded it. Okay. Now, after a second fold, some students will have a tendency to think that it's 0.012 because we're just going to go up by 0.004 each time. But that's not quite the case. Okay, if after 1 fold it's 0.008 and there's 2 layers, well, now I fold those 2 layers in half and I have 2 layers on top of 2 layers. I have 4 layers. So this is actually going to double in terms of its thickness to 0.016. Using that same approach, 0.016 will double to 0.032, which doubles to 0.064, which doubles to 0.128, which doubles to 0.256. And so we can see that after 6 folds already, we're only at 1/4 of an inch thick. Okay, after 6 folds, we're 1/4 of an inch in terms of thickness or in terms of height. So option A tells us here or part A, determine the least squares regression line for the data. In other words, if I were to make a scatter plot of these points, what would be the line or the equation of the line that best fits that data? Define any variables used, also find the correlation. Okay, so remember, in order to do this, we would put that data into list 1, and you don't have to do this if you don't want to. Just kind of follow along and get that information from me, but if you want to do it for the practice, you may. So list 1, you can see I've got the 0 to 6 folds with those corresponding thicknesses, 0.004 all the way down to 0.256. So if I want to calculate the least squares regression line, I hit my stat button, I slide over to calc, and then I choose option 8, lin reg a plus bx. This function of the calculator will tell me what is the equation of the line of best fit for my data. So my x list is list 1, my y list is list 2, and when I hit calculate, I get y equals a plus bx. There's my linear regression model. I can see that my a value is negative 0.04, and my b value is 0.037. So if I write those in really quickly, I get y hat equals, my a value is negative 0.04 plus 0.037x. However, it asks us to define any variables used. So instead of calling this y hat, we're going to call this height hat. And instead of calling this x, we're going to call that number of folds. Okay, so what does that mean in layman's terms? It means that the predicted height is going to equal negative 0.04 plus 0.37 times however many folds we have. Now, as far as our correlation goes, that's also there on our calculator. We get 0.88. Remember, correlation is a value from -1 to 1 that gives us strength and direction. The closer the absolute value is to 1, the stronger the relationship. So this is 0.88, so pretty strong relationship here. Now, B, does a linear model appear to be appropriate for this data? Explain why or why not. So what this is basically asking us to do is to look at the data as a scatter plot or as a residual plot, and I'm going to show both. Just because there's a strong correlation here, it doesn't necessarily mean it's linear. We saw an example of that in a previous lesson where we saw a very strong correlation, but we saw a curved pattern. So if I go to my scatter plot for list 1 and list 2, zoom 9, okay, I can see that my pattern of the dots is curved in an upward direction. Okay, and if I want to confirm that, I can go to my calculator and make a residual plot instead. So instead of my y list being L2, I can make that my residuals And now that I've got my residual plot, I can see that there is a curved pattern in my residual plot. I see that smiley face pattern. Okay, so to answer this question, does the linear model appear to be appropriate for this data? No. There is a curved pattern in the residual plot. Or if you were to just go with the first option and just say there's a curved pattern in the scatter plot, that's also an appropriate answer to do. But long story short, we see that our dots weren't forming a linear pattern. Now, even though we know it's not a linear pattern, just for fun, let's say, or let's determine what would our linear model predict for the height after 50 folds. Okay, we know it's not linear, but let's just see what we get. Okay, the predicted height is going to equal negative 0.04 plus 0.037 times the 50 folds. And if we do that, negative 0.04 plus 0.037 times 50, we get 1.81 inches. So what we're going to see is how close is our linear prediction compared to what is appropriate. Okay? And so in this case, we're going to look at a different type of growth. Instead of linear growth, we're going to talk about something called exponential growth, which should not be new to anybody. In exponential growth, what we're looking at is a relationship in which the values of the y are growing or shrinking, which we call decaying, based on repeated multiplication. Okay, so linear was repeated addition or subtraction. When you think about your slope, we're adding this every time x goes up by 1. We're adding 6, and then 6, and then 6. We're adding it over and over again. However, in exponential growth, instead of adding 6 each time, we're going to multiply by 6 each time. Or we're going to multiply by 2 each time to get the new value. Okay? And that's kind of what we're doing here is we multiplied by 2 to get to this. We multiplied by 2 to get to this. We multiplied by 2 to get to this because we were doubling in thickness each time. So we had repeated multiplication. Now, we said that a linear model was that y equals a plus bx. That's our framework for a linear model. For an exponential function, our framework is y equals a times b to the x. Notice x, our variable, our explanatory variable, is the exponent here. Now, what do a and b represent? Y and x are still the same thing. Y is our predicted outcome. X is going to be the explanatory variable value. A is our initial value. What are we starting with? Okay, that's what A is. Okay, and then B is what we call our scalar multiple. Okay, what are we multiplying by each time? Okay, that's what B is. All right, so we'll come back to this model in just a moment. Now, something that AP readers love to, or AP, College Board, whatever you want to call them, love to ask about is this next concept here. If a relationship displays exponential growth, what we can do is we can take the log or the natural log, which remember is ln, of the y values. Okay, another way that this is said is that for exponential growth is x versus log of y, or x versus the natural log of y. That's kind of some phrasing that they use. So we're not using x and y for our scatter plot. We're going to use x and the log of y, or we're going to use x and the natural log of y. And I'm going to show you what that looks like in just a second. Okay, so that's a relationship to remember. Exponential is x versus the log of y's. So if we do this, if we take the log of the y values in example 1 and create a new scatter plot with this data, what do we notice? So I'm going to go back to my calculator here, and I'm going to go stat edit, and I'm going to highlight list 2. I'm going to press enter. And what I'm going to have now for list 2 is I want to take the log, which is about halfway down the first column. You'll just see a button that says log. I want to take the log of list 2. So list 2 is going to turn into the log of list 2. I press enter. And you can see that I've got brand new values in there. Now if I make a scatter plot of this new data, notice what my scatter plot looks like now. This is not x and y. This is not our original number of folds in thickness. This is the number of folds with the log of the thickness. Okay? And we can see that our scatter plot is now a straight line. This is what we're talking about when we get to this concept, transforming to achieve linearity. I took the log of my y values to create a straight line. Okay. So how do we answer this? We created a scatter plot. What do we notice? The scatter plot is now linear. Okay. Now, it says to determine the least squares regression line of the new data. Okay, so without altering it, I'm now going to take the least squares regression line. Of course, there's going to be an add. But I'm going to take the least squares regression line of L1 and L2. Remember that L1 hasn't changed, but L2 is now the log of my y's. And if we look, that correlation is now perfect. Okay, but I've got y equals a plus bx. Y hat equals negative 2.4 plus the log, 0.3x. Okay. However, one thing we want to note is that this x is my number of folds. But this y isn't just the height. It's the log of my predicted height. Okay? So that's one thing that you might have to remember is after you take the log of your y's and you get your straight line, and now you get your new least squares regression line, we want to make sure that we talk about that it's the log of our height, or it's the log of our y values that gives us this. Okay? Now, something that we won't do just because we're not in person, we're doing a video. This takes a little bit longer to do, and I don't want to waste video time on this. But we do a little bit of work with logarithms and undoing, and perhaps if you want to experiment on your own, or if the teacher in the room wants to walk you through the process, we can basically work backwards and get this into this form right here. But that's not something that we are going to do in the video. But long story short, we're going to jump to C here, and it says use the exponential model to predict the height of a piece of paper after being folded 50 times. So what we could do is we could plug our 50 into this, and we would get our answer, but we'd still have this log out here in front that we would have to account for. So instead, what we're going to do is this. On our calculator, I want to go back to my original data. So the way we unlog something is on your calculator, you're going to do second log list 2. If we do 10 to the power of something, that undoes a log because a log has base 10. Some of this may sound familiar, some of it may not. No big deal. You don't need to worry about this. Okay? But you can see by me doing that, I send all the information back. This is not something you need to worry about. So if you're confused, how did he do that? Don't worry about it. Okay? I'm going to take my original data. And what I saw was that in my original data, I saw that my blue dots there were not linear. So if I go stat calc, you can see that option 8 was the one that we use, but we also have an option 5. We have an option 6, a quadratic regression, a cubic regression, a quartic regression. But if I keep going down, you see that option 0 is EXP, exponential regression. And this problem asks us here, use the exponential model to predict the height of a piece of paper after 50 folds. So what I'm going to do is this. I'm going to choose the exponential model for list 1 and list 2. And remember the form of exponential we said was y equals a times b to the x. When we look here on our calculator over on the right-hand side, y equals a times b to the x. Okay. And so let me pull this up side by side. So my exponential model, y hat equals a times b to the x, but my y hat is height. Remember, I went back to my original data. So it's not log of height. I went back to my original. Equals a, which is 0.004, times b, which is 2 to the x, which was number of folds. Now, we should have been able to come up with this from the get-go when we said a, the number out in front, is the initial value. Well, what did we say was the initial thickness of a piece of paper? 0.004 inches. B, which is the base here, is our scalar multiple. What are we going up by each time? What are we multiplying by? 2. Our original piece of paper was 0.004. We were doubling its thickness every time we folded. Okay? So what we're going to do then is we're going to do 0.004 times 2 to the 50th. And we're going to see what we get. 0.004 times 2 to the 50th. And we get 4.5 times 12 or times 10 to the 12th. 4.5 times 10 to the 12th inches. In other words, that is 4, and then we slide the decimal place over 12 times to the right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 1,000, million, billion, trillion, 4.5 trillion inches. Now, you may not be believing me. So let's just take this from a more practical approach. This times 2. This is one fold. 2 folds. 3, 4, 5, 6. Now, a quarter of an inch is going to double to half an inch at 7. Half an inch is going to double to an inch at 8 folds. 1 inch to 2 inches at 9. That doubles. 4 inches at 10 folds. 4 doubles to 8. 16 inches. 32 inches. 65 inches. 131 inches. 262 inches. And so on and so forth. And we can see that this concept of doubling each time we fold is just going to go more and more and more. I'm going to see if I can get us to where we were. Okay, that's where we were. So this is our 50 folds. So this is inches. So let's go ahead and divide that by 12. This is how many feet that is. 3.75 times 10 to the 11 feet. Well, there's 5,280 feet in a mile. So this is, let's see, 71 million miles is how tall our piece of paper would be after 50 folds. 71 million miles. Kind of fun. Okay, if you don't believe me, I don't know what else to tell you. But obviously you cannot fold a piece of paper in half 50 times. But if you could, that's how tall it would be when stacked on the ground. Okay, enough to go around the world countless times. Okay. So let's go ahead and try one example a little bit faster now on your own with exponential growth. In 2014, a lake began with 1,200 fish. After being subjected to a virus, the population of fish began to decrease. The following table shows the years after 2014 and the population of fish in the lake. So in 2014, there were 1,200 fish. And then each year subsequently, we can see that the fish population is decreasing. So what form does the scatter plot display? So for the sake of time, I actually put this data a little bit later on into list 4 and list 5. So if I make a scatter plot of list 4 and list 5, I hate that box plot comes on every time. There we go. So there's our scatter plot. Once again, we can see that curved nature of it. Okay, it's going down quickly, and then it starts to flatten out down at the bottom. So what form does the scatter plot display? Nonlinear. Okay, if nonlinear, take the log of the y values to achieve linearity. So if I go back to stat, edit, and I go to list 5, I take the log of my y values. Okay, so I just go up to list 5 and press enter. So I've got my cursor. List 5 equals the log, again over on the left-hand side, of list 5. Okay, there's all my log values. Now, if I just clear out of here and I hit zoom, one day I'll just pay and get the free or the premium version. But if I clear out of there, now I can see that my scatter plot, after taking the log of the y values, I've now transformed my data to achieve linearity. Okay? So, because x versus the log of y, x versus the log of y is linear, therefore, this is exponential. The log of y, x versus the log of y is linear. This is an exponential model. So how many fish would be appropriate, how many fish would the appropriate model predict to have in the lake at 2023? One common mistake students will make is before we do that, let's get our equation. We know it's going to be y equals a times b to the x, right? We've determined this is a linear model. So I want to go back to my original data. So remember the way to do that? To unlog, we just simply second log our list. Okay? And that sends everything back to where it was. Stat, calc, I want my exponential regression, but I want it for list 4 for me. Oh, this is not fun. List 4. There we go. List 5. And I can see that I get y equals a times b to the x, where y is the population of fish. So the predicted fish population is 1189.9 times 0.61 times x years after 2014. Now that we have that, it still didn't answer the question. How many fish would the model predict? So, common era students will take that 2023 and they'll plug it in here. Okay, remember that X is the years after 2014. Therefore, 2023 is going to be 9 years after. So 1189.9 times 0.61 to the 9th. 1189.9 times 0.61 to the 9th. 13.9. Okay, so essentially, because we're talking fish, the model predicts that in 2023, there will be about 14 fish left in this lake. Okay. So as a quick summary, not every relationship that we have is linear, but we want things to be linear because it's the easiest to work with. Correlation only works for linear models. So we might have to transform our data in order to achieve that linearity. So the first type of relationship we focused on was an exponential model. And in an exponential model, y equals a times b to the x, where a is our initial value, x is our scalar multiple. What are we changing by each time? The relationship in an exponential model, in order to make it linear, is x stays, but we take the log of our y's or the natural log of our y's. It works the same way. And when we determine that x versus the log of y is a straight line, now we know it's an exponential model. Therefore, we can use the exponential model function on our calculator to get the equation of that model and then plug in our values to get our corresponding answers. Okay? If you have any questions, as always, please feel free to reach out. Otherwise, I'll see you next time. Take care, everybody.